Okay, this title is kind of silly, but I need to talk about light, and I need a whole bunch of stuff. And so I have this old presentation. I'm just going to go through this and post it as a video. And if it's terrible, I don't even know what's on each slide. So you're gonna be as surprised as I am. Okay, so what is a wave? I do know this. I remember I made this a long time ago. So this is my example of a wave. These are people, and some are sitting down and some are standing up. This is my representation of a wave at a football stadium, so that we can use that to talk about waves. So in general, in a wave, a person in the football wave, okay, it could be a soccer game, it could be a baseball game, but I'm just using football. The people move up and down like that, okay, but the displacement moves to the side. So you have these two things in a normal wave. You have the displacement and the people, the medium, okay, and they don't have to move the same way. What if you have a repeating wave? So let's suppose that people stand up and sit down alternatively, and they move along in this way like that. So what can we measure about this? First thing we could do is measure the wave speed. If you looked at the speed of a displacement moving, okay, so it's not the person. The wave can travel all the way around the stadium in probably, a minute. But the person's not going all the way around in a minute. That'd actually be a pretty fast person. Okay, so that's the first thing, the wave speed. Excuse me. The next is the wavelength. Sorry, I'm behind. The next is the wavelength. This is the distance from one displacement to the next displacement. So this works for a repeating wave, and so it'd be measured in meters. We use the Greek letter lambda to represent wavelength. The next is the frequency. So if I looked at how often, how many of these displacements pass some fixed point every second, that would be my frequency. I use the symbol F for this. And so then we get this relationship between the frequency, the wavelength, and the frequency. The velocity of the wave is equal to the wavelength times the frequency. And that's true for any repeating wave. Now we also have this, the amplitude. The amplitude of a wave is the maximum displacement from equilibrium point. So if you looked at kind of the middle point for these people moving up and down to the highest point, that would be your amplitude. Okay, and yeah, the people thing doesn't completely work here, but come on. This is an animation from something, but I don't know. It's the same thing, so we don't need to look at that. Here's another animation. There's a great applet, actually. You can go play with these, but it's just talking about waves on a string. Now there are two kinds of waves. There's a transverse wave. So imagine a slinky, and I shake the slinky side to side, and the displacement travels the length of the slinky. That's a transverse wave. But I could also push the slinky in the direction of the slinky and compress the slinky, and that compression moves along the wave. So in that case, the displacement is in the same direction as the wave, and that's a longitudinal wave. Now we really care about transverse wave because we're really talking about light. Wave power and intensity. So if I have a point source and that point source produces a wave and that wave spreads out in all directions, then even there's energy there, right? And energy per time is power. But as you get further and further away, that power is spread over a larger and larger sphere. So for a point source, an ideal point source, we measure the power per area as the intensity. So as it moves further and further away, the area of that sphere, 4 pi r squared is the area of the sphere, gets larger. So in general, for a point source, the intensity I is the power of the source divided by the area, which would be 4 pi r squared. Okay, here is a idea about superposition. We talked about superposition of electric and magnetic fields. Well, you can have superposition of waves too. So if I have this string, on the top picture it's a string, and the two waves are coming towards each other. When the two waves are right on top of each other, they just add together. And we call that constructive interference. And then you could also have the opposite happen. You could have an up wave and a down wave. When the two waves hit each other, they cancel, and that's destructive interference. Now this is again a wave on a string. If I take this string and I shake a wave down the string and it gets to the end and that end is fixed, then what happens is that the wave gets inverted. Okay, so when it hits a fixed string, the wave reflects back but is inverted. And there's an applet for that. Now, if it was a loose string, if it wasn't tied, like fixed, it would actually not be inverted. But the key thing is waves do reflect. Waves also refract. Okay, refraction is when a wave enters a medium of a different speed at an angle, and it actually turns. But I don't want to really talk about this too much right now. Wave on a string, I don't want to talk about that. These are some questions. Two waves traveling, standing waves. Standing waves, we're not really going to worry about that. Maxwell's equations, I don't want to go over this in super detail. I made another video on that. But these are the 4 equations that relate electric and magnetic fields to charges and to each other. Okay, and we've kind of gone over Faraday's law. We didn't write it in this form. I know it looks scary, so just don't worry about that. I've already talked about this, but Gauss's law basically tells you how to find the electric field due to a point charge. That's what it is. Gauss's law for magnetism is one that's kind of weird. It says that essentially it says the same thing for magnetic fields, but the difference is that you can't have an individual magnetic charge. We'd never found that, and that would be called a magnetic monopole. So Gauss's law for magnetic field says we've never found a magnetic monopole. But if it did, it would work. We just have to change the equation a little bit. Faraday's law, you've seen this one. This says that a changing magnetic field creates an electric field. And so that electric field could create a current, doesn't have to. Okay, so a changing magnetic field produces a curly electric field, and which is really different than the electric field due to a point charge, which is just points directly outwards. Okay, a curly electric field looks actually like the field pattern due to a magnetic field. Ampere-Maxwell law just says that it says that in order to make these weird situations work, which I'm not going to talk about, you have to have the same thing true. A changing electric field makes a curly magnetic field. So let me go back because it's important. A changing magnetic field makes a curly electric field. A changing magnetic field makes a changing electric field makes a changing curly magnetic field. So they do the same thing to each other, which is really nice. Makes me happy. So here's just a way you can show that you can have this region of space with an electric field and a magnetic field, and it can move and support itself. The changing electric field will make a magnetic field, and the changing magnetic field will make an electric field, and everything works if that piece of space moves at a certain speed, the speed of light. But I'm not going to talk about that. So here it is, moving at the speed of light, electric and magnetic field. How do you make an electromagnetic wave? So here's an electric charge. If I accelerate that charge, then it changes the electric field, which changes the magnetic field, and you get light. So this is actually what it would look like. I mean, you can't really see this. And it's not traveling at the speed of light because you wouldn't be able to see it. So that's an an electromagnetic wave is a changing electric and magnetic field due to an electric charge that's accelerated, and that's what light is. It is an electromagnetic wave. So if I move this charge up and down, I create a changing electric field, and that changing electric field moves with the speed of light, c. And it doesn't matter what wavelength of wave you're making here. There's the wavelength. So here is something really important. All electromagnetic waves travel at the speed of light. Different wavelengths interact differently with matter. So if I have a radio wave, it will go through glass, it will go through bricks. That's why your phone, which essentially uses radio waves to contact the cell tower, it works inside. It works through glass. Okay. Visible light goes through glass, but it doesn't go through bricks. So those radio wave and visible light are really physically the same thing. They just have different wavelengths, which leads them to interact differently with matter. So light is indeed a wave. And so here's a picture of some waves in water. I actually made that just for you. Actually, it was a long time ago. So it has wavelength, it has amplitude, it has wave speed, and it has a frequency. Here's a good animation of how you make radio waves. So if you have an antenna, which is a wire, and you accelerate electrons up and down, which is an electric current, then you can create these radio waves. So a radio wave This could be KSOU, which is the Southeastern Radio. Okay, and then it's complicated, true, but inherently it's an accelerated charge that makes these radio waves. This is the spectrum, the electromagnetic spectrum. So here we'll start off with really, really short wavelength. We call those gamma rays. And then we get longer and longer wavelengths, X-rays, ultraviolet. And then there's this very, very, very narrow band of wavelengths that we can detect with the eye. We call that the visible spectrum. And then as you get larger than that, we call that the infrared, and then microwave, and then radio. So, yeah, but those are all physically the same mechanism for the interaction between electric and magnetic fields. Infrared, I'm a huge fan of. This is an infrared camera, so it detects the infrared light, and you can actually see things that are different temperatures, because different temperature objects give off infrared light of different wavelengths. So detecting the wavelength of light tells you something about the temperature. This is a coffee pot, and there's a whole bunch of cool stuff here. I thought I had a video. Oh, this is a video. Here's me pouring the coffee. I watch. Wait for it. The cup starts getting warmer, because on the outside you can't see through the cup, but the cup gets warmer, you can see it warm up. I'm not giving a commercial for these infrared cameras, but 10 years ago you couldn't have gotten a camera for less than $3,000, $4,000. But now the price is much lower, and they have these little cameras you can connect to your phone, and it's just awesome. How do you find the speed of light? I guess we'll go through this quickly. So originally Galileo wanted to calculate the speed of light, and what he did was he held out a lantern, and he turned on the lantern. He had someone on a hill far away, and when they saw the light, they turned on their lantern, and he tried to measure the time between the light going there and back. It turns out that you can't do this, because the light travels so freaking fast that all you're getting is the delayed time and the reaction time. You can't really measure it. It's not far enough away. Here's another way to do it. So what you do is you take a light source and you pass this like wheel with teeth in it, and the light goes through an opening in the teeth and reflects off a mirror. If you time the speed of this wheel just right, then the light will go down and it will reflect off the mirror and come back and pass through a tooth and not get blocked. But if you have the wrong speed of the by adjusting the speed of the spinning wheel until you can see the light again, you can measure the speed of light by how far, the speed of the wheel, how far away the mirror is, and you can determine the speed of light. And then we actually do this in advanced physics lab, and it's kind of cool. Here's a better and really cool way to calculate the speed of light, and this was one of the ways I did it. So they look at the moons of Jupiter, and if you look at the moons of Jupiter that orbit, and you can actually see these with binoculars, you should try it out. So here is a rough representation of the green dot being Earth in December, and the green dot is Earth in June. It's orbiting the sun, the big yellow dot. And then the red dot is Jupiter, not to scale. Okay. And so if you look at this orbital period for Jupiter, when in December versus June, then light has to travel a different distance. It's actually more complicated than that, but this gives you a rough idea of how that would work. And then so by using these super large distances, which we knew, we can measure these with astronomy. You can use that to determine the speed of light. Kind of cool. Here's a little animation of light coming from Jupiter to the Earth, and you can see it takes less and less time. And I made a little graph, and I don't really want to talk about this stuff because it is cruel, but I guess I should talk about atoms. Nah. Nucleus, proton. Nah, I'm not going to talk about this because I just want to talk about light, right? What else do I need to talk about with light? Light of different photoelectric effect. Okay, I think that's enough. Okay, so there's your short introduction to light. I'm going to make another video about things like polarization, lenses, images, and stuff like that. Okay, that's it.